At first glance, the island looked like it was already gone. A narrow strip of land, once vibrant with life, now reduced to fractured edges and collapsing shorelines. Waves advanced relentlessly, biting into its borders, carrying away grains of sand that had taken centuries to accumulate. With each passing storm, the island seemed to shrink, its future measured not in years but in tides. From above, the transformation was unmistakable. Satellite imagery revealed a slow but undeniable disappearance. What had once been a thriving ecosystem, home to dense vegetation, nesting birds and intricate coastal biodiversity, was now on the brink of vanishing beneath the rising sea. And yet, in the face of this inevitable loss, an extraordinary decision was made. More than 3 million tons of sand would be brought in, pumped, transported, and reshaped onto the dying island in one of the most ambitious environmental interventions ever attempted. But could an ecosystem be rebuilt so artificially? Could something so fragile be restored with something as simple as sand? Or would this massive effort only delay the inevitable? To understand the scale of this transformation, it is necessary to look back, before the machines arrived, before the sand began to flow, when the island still functioned as a delicate, interconnected system. Barrier islands like this one are among the most dynamic landforms on Earth. Formed by the accumulation of sand deposited by waves and currents, they exist in a constant state of change. Unlike solid landmasses, they shift, migrate, and reshape themselves over time, responding to wind patterns, ocean currents, and rising sea levels. This constant motion is not a flaw, it is essential to their survival. In their natural state, barrier islands act as buffers between the ocean and the mainland. They absorb the energy of storms, reduce coastal erosion, and create sheltered environments where unique ecosystems can thrive. Salt marshes, dunes, and tidal flats all depend on this delicate balance. But in recent decades, that balance began to unravel. Sea levels, driven by global climate change, started to rise at an accelerated rate. Warmer oceans expanded, and melting ice sheets added billions of tons of water into the system. At the same time, human activity along coastlines disrupted the natural flow of sediment. Dams trapped rivers that once delivered sand to the shores. Coastal development prevented dunes from migrating inland. Protective structures, designed to shield infrastructure, inadvertently starved beaches of the very materials they needed to survive. The result was a slow but persistent erosion. For this island, the consequences were devastating. Storm surges began to breach its defenses, carving channels through its core. Vegetation, once anchored in stable soil, struggled to take root. Nesting grounds for birds disappeared. Tidal patterns shifted, altering salinity levels and disrupting marine habitats. What remained was a fragmented landscape, an ecosystem on the verge of collapse. Scientists monitoring the island observed a critical tipping point approaching. Without intervention, models suggested that within a few decades, the island would be entirely submerged, leaving behind only open water where life once flourished. The loss would not be isolated. Barrier islands protect vast stretches of coastline. Their disappearance would expose inland areas to increased flooding, stronger storm impacts, and irreversible ecological damage. Faced with this reality, a bold proposal emerged. If the island could not sustain itself naturally, perhaps it could be reinforced, rebuilt from the ground up. The concept was deceptively simple: restore the island by adding sand. But the scale was unprecedented. More than 3 million tons of sediment would be dredged from the ocean floor, transported through pipelines, and carefully deposited onto the island's eroded surface. Engineers would reshape the land, reconstructing dunes and restoring elevation. Vegetation would be replanted to stabilize the soil, while natural processes would be encouraged to take over once the foundation was rebuilt. It was not merely an act of construction. It was an attempt to restart an ecosystem. Yet from the beginning, the project was surrounded by skepticism. Critics questioned whether such an intervention could truly replicate natural processes. An island is not just sand, it is a living system shaped by countless interactions between organisms, water, and climate. Could a man-made reconstruction ever achieve the same complexity? Others raised concerns about unintended consequences. Dredging the ocean floor could disrupt marine habitats. Altering sediment flows might affect nearby coastlines. And there was no guarantee that the newly deposited sand would remain in place, especially in the face of powerful storms. Even among scientists, opinions were divided. Some viewed the project as a necessary experiment, a chance to test whether large-scale restoration could counteract the effects of climate change. Others saw it as a temporary solution, one that might buy time but not prevent ultimate loss. Despite these uncertainties, the project moved forward. Massive dredging vessels arrived offshore, their machinery designed to extract sediment from the seabed with precision. Long pipelines stretched toward the island, carrying a continuous flow of sand mixed with seawater. Day after day, the island began to change. What had once been a narrow, eroded strip expanded outward. New layers of sediment accumulated, raising the elevation above sea level. Engineers sculpted dunes to act as natural barriers, carefully mimicking the shapes formed by wind and waves. From a distance, the transformation was dramatic. But up close, it was still incomplete. The sand was raw and unstable. Without vegetation, it remained vulnerable to erosion. Wind carried fine particles across the surface, reshaping the terrain in unpredictable ways. Tides carved small channels, testing the resilience of the newly formed land. For months, the island existed in a fragile state, rebuilt but not yet alive. Then, slowly, the first signs of change began to appear. It started with the smallest of pioneers. Microscopic organisms, carried by water and air, began to settle on the sand. Algae formed thin films across damp surfaces, stabilizing the top layer. Seeds, transported by wind and birds, found their way into sheltered areas. At first, growth was sparse. A few scattered plants emerged, their roots anchoring into the loose sediment. These early colonizers, species adapted to harsh coastal conditions, played a critical role in the island's recovery. Their presence reduced erosion, trapped additional sand, and created microhabitats where other organisms could survive. Yet the process was far from guaranteed. Storms continued to test the island's resilience. Each wave had the potential to undo weeks of progress. Sections of newly deposited sand were washed away, forcing engineers to adapt their approach. And still the question remained. Was this enough? Could a system so carefully engineered truly sustain itself in the long term? Or was the island destined to remain dependent on continuous human intervention? As months turned into years, researchers returned to the site, documenting every change. They measured sediment stability, monitored vegetation growth, and tracked the return of wildlife. At first, the changes were subtle, barely noticeable to the untrained eye. But beneath the surface, something far more significant was beginning to unfold. At first, the transformation remained almost invisible. From a distance, the island still appeared as a reconstructed landscape, an engineered form imposed upon nature. But beneath the surface, within the grains of sand and the shifting patterns of water, a quiet chain reaction had already begun. The early colonizing plants, once scattered and fragile, started to expand. Their roots penetrated deeper into the sediment, binding loose particles together and increasing resistance against wind erosion. As these pioneer species grew, they altered the microenvironment around them, trapping moisture, reducing surface temperatures, and accumulating organic material. This seemingly small shift marked the beginning of ecological succession. Within a year, patches of vegetation became clusters. Within 2, those clusters began to merge. Grasses adapted to saline conditions spread across the dunes, forming dense networks that stabilized the island's surface. These grasses acted as natural engineers, capturing airborne sand and gradually increasing the height and strength of the dunes themselves. With structural stability improving, a new phase of recovery emerged. Insects were among the first to arrive in greater numbers. Carried by wind currents or drawn by the emerging plant life, they introduced new biological interactions into the system. Pollination processes began to take shape. Nutrient cycles, once disrupted, slowly restarted. And then came the birds. Initially, they appeared only briefly, resting during migration, testing the safety of the newly formed land. But over time, their presence became more consistent. Shorebirds returned to forage along the tidal edges, probing the sand for small invertebrates that had begun to repopulate the area. Soon after, nesting behavior was observed. This marked a critical milestone. Birds are highly sensitive to environmental conditions. Their decision to nest indicated not just the presence of food, but also a level of stability and safety within the habitat. Eggs laid in the dunes represented a profound shift, from a transient landscape to a functioning ecosystem. Beneath the waterline, changes were unfolding as well. The newly restored shoreline began to influence wave patterns and sediment distribution. Tidal flows adjusted to the island's expanded form, creating calmer zones where fine sediments could settle. In these protected areas, seagrass beds started to emerge. Seagrasses are among the most important components of coastal ecosystems. They provide shelter for juvenile fish, stabilize the seabed, and play a significant role in carbon sequestration. Their return signaled a broader ecological recovery, one that extended beyond the island itself and into the surrounding marine environment. Fish populations soon followed. Small species appeared first, taking advantage of the new habitats. Larger predators arrived later, drawn by the increasing availability of prey. The food web, once fragmented, began to reassemble layer by layer. Scientists monitoring the site documented these changes with increasing interest. Data collected over several years revealed measurable improvements in nearly every ecological indicator. Vegetation cover increased by over 60% compared to the immediate post-restoration phase. Sediment retention rates improved significantly, reducing the island's vulnerability to erosion. Biodiversity indices, used to measure the variety and abundance of species, showed a steady upward trend. Perhaps most striking was the island's response to storms. In the years following the restoration, several major storm events tested its resilience. Where previously such storms would have caused catastrophic erosion, the reconstructed island absorbed the impact more effectively. The dunes, reinforced by vegetation, acted as natural barriers. While some sand was lost, much of it was redistributed rather than removed entirely. In some cases, the storms even contributed to the island's evolution, reshaping dunes and redistributing sediment in ways that mirrored natural processes. This adaptive response suggested something remarkable. The island was no longer just a constructed landform. It had begun to behave like a natural system. Yet not all outcomes were entirely predictable. In certain areas, the accumulation of sediment altered tidal channels, affecting nearby ecosystems. Some species thrived more than expected, while others were slower to return. The balance, though improving, remained dynamic and in constant flux. This raised important questions among researchers. Was the restored ecosystem truly equivalent to its original state? Or had a new, entirely different ecological system emerged? Long-term monitoring became essential. Over a decade, the data revealed patterns that extended beyond immediate recovery. Carbon storage within the island's vegetation and surrounding seagrass beds increased significantly, contributing to climate mitigation efforts. Coastal protection improved, with inland areas experiencing reduced flooding during storm surges. Economically, the benefits were also evident. Reduced damage from storms translated into lower costs for coastal communities. The return of biodiversity supported fisheries and, in some cases, ecotourism. What had begun as a costly and uncertain experiment started to demonstrate tangible, measurable value. But perhaps the most profound impact was conceptual. This project challenged long-standing assumptions about environmental restoration. For decades, conservation efforts focused primarily on preservation, protecting what remained of natural systems. Intervention at such a massive scale was often viewed with caution, if not outright opposition. Yet here was a case where deliberate, large-scale action had not only halted environmental decline, but initiated recovery. It suggested that, under certain conditions, human intervention could align with natural processes rather than oppose them. Still, the lessons were not universal. Not every ecosystem can be restored in this way. The success of this island depended on specific factors: availability of sediment, understanding of local dynamics, and continuous scientific monitoring. Without these, similar projects could fail or even cause unintended harm. As global sea levels continue to rise, the implications of this experiment extend far beyond a single island. Coastal regions around the world face similar threats. From low-lying delta systems to densely populated shorelines, the loss of natural barriers could have far-reaching consequences. The question is no longer whether intervention is possible. It is how, when, and where it should be applied. In the years since the sand was first pumped onto